All right, we're at section 13.6, energy considerations in planetary and satellite motion. If we look at this uh, slide, we know that uh, if an object moves from A to B, well, if there's motion, there's got to be velocity, so there's kinetic energy, and we can see that it is at R initial, it's closer to the Earth. At R final, it's further. So it's gained some gravitational potential energy. And so we're going to look at those energy considerations in planetary and satellite motion. So we see here that the total energy is equal to kinetic energy plus gravitational potential energy. So the E is equal to 1/2 mv squared minus the uh, GMM over R. Remember the GMM over R, not the R squared. We're not talking about the force. We're talking about the gravitational potential energy. We saw that in uh, the last section. The gravitational potential energy is minus GMM divided by R. So the change in kinetic energy plus the change in gravitational potential energy is equal to zero. In other words, the isolated conservative forces, the total energy is going to uh, remain zero. So the change in kinetic energy is going to, plus the change in potential energy is going to equal zero, which says that the uh, initial energy is going to equal the final energy. So 1/2 mvi squared minus gmmri is equal to 1/2 mv final squared minus gmm rf, so the final distance. Um, so we also know that force equals mass times acceleration. What is the gravitational force? It's gmm over r squared. And what is mass times acceleration? Well, the acceleration in this particular case is the centripetal acceleration, um, which is v squared over r. So that's the right hand side of the equation. So gmm over r squared is equal to mv uh, squared over r. But let's multiply both sides by r. That'll make this one just, that'll take care of the squared term, and that'll get rid of the r, and we'll have 1/2 mv squared. Well, that looks familiar, doesn't it? 1/2 mv squared, that's kinetic energy, equals gmm over 2r. So E is equal to gmm over 2r minus gmm uh, over r. So they're equating this as the kinetic energy. They're saying this is kinetic energy, that's the total energy. So for circular orbits, E is equal to minus gmm over 2r. Uh, and for elliptical orbits, E is equal to gmm over 2a. Well, what is A? A is the semi-major axis. If you have an ellipse, um, the semi-major axis is the long axis. A is from the center to the center of the ellipse to the outer edge. So B is the semi-minor axis from the center up to the small diameter, if you want to call it. Okay, let's take a quiz. But before we take this quiz, let's go back on a previous uh, slide. Um, uh, we talked about um, the nice little Wikipedia uh, demonstration of basically they're showing Newton's second law, where the area, the purple area mapped out for equal periods of time is the same, and it's good to see that on this side we have the perihelion, where the approach is closest to the, in this case, Earth or Sun or whatever. Well, if I use the word perihelion, it's got to be the Sun. If it were the Earth, it would be perigee. So if I'm talking about perihelion, this is the Sun and this is a planet or a comet, or we'll probably say a comet because none of the planets, I believe, are this eccentric. Um, so at the perihelion, the, the total energy remains the same, but here it's you can see the vector, the green vector of velocity is the greatest on this side. So this is where the kinetic energy is the greatest, and the potential energy is less here just because of the distance is less. On this side, the aphelion, some people say aphelion. I like aphelion because I like to keep the helio in there for the sun. The aphelion is the kinetic energy is the smallest. You can see that the green arrow is the smallest at this point. So the gravitational potential energy is the greatest over here at the aphelion. Kinetic energy perihelion, kinetic energy is the greatest at the perihelion. The potential energy is greatest at the aphelion. Okay, now that we've done that, let's go back to the slide and look at this quick quiz. A comet moves in an elliptical orbit around the sun. At which point in its orbit, the perihelion or aphelion represents the highest value of the speed of the comet? If the highest speed comes from the highest kinetic energy, remember 1/2 mv squared, so the speed would be greatest at the perihelion. And sure enough, perihelion, there's the answer. Okay, let's look. A comet moves in an elliptical orbit around the sun. Which point in its orbit, perihelion or aphelion, represents the highest value of the potential energy of the comet's sun system? Well, I just said when the velocity is smallest, which is at the aphelion, kinetic energy. When the kinetic energy is smallest, the potential energy is the highest. So it's at the aphelion. Oops, there it is. There's the answer. Now let's look at a comet moves in an elliptical orbit around the sun. Which point in its orbit, perihelion or aphelion, represents the highest value of the kinetic energy of the comet? I thought we already did that one. The kinetic energy is highest at the perihelion. Did I go backwards? Let's see. Oh, one asked the speed. I'm sorry, asking the speed. Well, the speed, you know, is related to the kinetic energy. So the speed is greatest at the perihelion. The potential energy is greatest at the aphelion. And the kinetic energy, which is related to speed, is also greatest at the perihelion. Now let's look at the last question. The comet moves in an elliptical orbit around the sun. Which point in its orbit represents the highest value of the total energy of the comet-sun system? Well, they're kind of throwing you off there because it's neither the perihelion or aphelion, because at every point, it's a constant exchange of kinetic energy and potential energy. So the total energy is constant. In one of my previous videos, I mistakenly said that the total energy is 0. That was a mistake. The total energy is constant, not 0. So at all points, the total energy of the comet is greatest. I mean, it doesn't change. It's this constant exchange of kinetic energy and potential energy. And I think I guess I'll go through escape speed. Let me see if I can remember it. We know that the energy is equal to 1/2 mv squared minus gmm divided by r. 1/2 mvi squared minus gmm r over e, where re is, I said r over e, re is the radius of the Earth, equals minus gmm r max, which is the potential energy. And v squared, that we solve for v squared, is equal to 2 gmme times 1 over re minus 1 over r max. So the escape speed is equal to r max becomes, as r max becomes greater, as this becomes greater, that, you know, whenever you have a fraction like this, as this gets greater and greater, this term becomes zero. It becomes insignificant. So we're left with 2 GMR times 1 over RE. So the escape velocity is the square root of 2 GME divided by RE, because the R max becomes insignificant. And here's some escape speeds. For the Earth, it's 11.2 kilometers per second. So that's 11,200 meters per second. Mercury, a small planet, 4.3 kilometers per second. Venus, 10.3. Mars, 5. You see Jupiter, 60. And if you look at the sun, from the surface of the sun, it's 618. Now, who's going to launch from the surface of the sun? But it's just that's a practical standpoint. The theoretical, the escape speed has to be 618 kilometers per second. And there are energetic particles escaping the sun all the time. You can have these coronal mass ejections where the sun just launches out the energetic particles, and that's when we see aurora borealis in the north, aurora australis in the south. So there are things escaping from the sun. There's escape speed. The escape speed is equal to the square root of 2 GM over R, where R is the radius of the planet or the sun that you're looking at. Okay, I'm not gonna go into supernova, neutron stars, black holes, or dark matter. If you're interested in those, you're welcome to study them. In the interest of time, I'm not gonna cover them. So we'll stop it here.